All right, can you all hear me okay? All right, cool. So on Wednesday, you have exam 2, and I sent you guys a copy, I think both PDF and a Word document of a practice exam. If you have questions regarding it, just let me know. I need to change my office hours tomorrow's office hours from 2 to 3. Okay. Something came up and I have to change it to that time. Okay. Do you have any questions regarding exam 2? You don't have a practice exam. Okay, well, I thought I did send one with a PDF. Okay, so let me, after my 2 classes today, I will send it, okay? I thought I did it. And I try not to put them on Canvas just because of issues with the, I have to do a lot of work to the exam just to be able to put it on Canvas. Okay. So that's why a lot of the documents I've been emailing to you instead of putting them on Canvas, just because of the amount of work I have to do just to put them on there. There's just a lot of regulations I have to deal with. So I apologize for that. And if there's ever a document that's misplaced that I email to you, just contact me. I can send it to you. I did create a new, I updated the DC Circuits Lab, a new version of it. So please make a note of that. The one change I made is when you wire up the circuit for the next lab, I want you to take a picture of it, incorporate it into your lab report. So I know this is lecture, not lab, but were there any problems in carrying out the experiment other than not having a diode? I'm guessing the large meter did not work well. That's not good. So one of the things that's come up that's bothered me is you guys have, I'm giving you several weeks to do the lab. Okay. Yeah, part of it for the bulb, we need to use alligator clips or something. So regarding, okay, so that's a good question. Here's the issue with the bulb. I think that power supply was at its limit. Well, it hit the power limit, basically. Right? They're rated based on power. So V times I, you're limited. It was limited, right? And I think that was the problem. Okay. But so there are issues with it. One was with that bulb, and I really wanted to use a little bulb like the ones for the multimeter quiz, but the problem is I tried it and burned one because 12 volts was too much for the bulb. So yeah, I mean, The bulb, I understand the issue with the bulb part. The other part, the Ohm's law part should have been pretty, should have worked fairly well because we weren't at the limit of the power supply. Well, the power, it depends on what your, the power rating is. It's V times I, that's the limit. In fact, a DC output, there's not even a power rating on here. I'm hoping it's 2 amps at 12 volts. Because if it's not, then at 12 volts, it might be something less. It doesn't say what the power rating is. I guess that assumes 2 amps at 12 volts. Because a lot of these are, well, it says 30 watts, so I guess that's okay. But I did find that it's not a well-regulated supply too when I was practicing with it. Okay, so anyway, the one big issue, the one big thing that bothered me was, you know, I had several people start on the lab yesterday when they had 2 weeks to do it. That ain't gonna work. That ain't gonna cut it in this class. This, you know, a lot of these labs, you're gonna be figuring things out. It's not gonna be something where it's not like a cookbook where you're gonna be just told how to do everything. Okay, so for the next lab, you want to start early. And then if you have trouble, you can contact me. We can set up a Zoom meeting or something, and then we can work on it. But if you do it the last minute, you're in trouble. So right now I have it, the next lab doing the 23rd, So let me talk about, when we talk about the lab Wednesday, I'll talk about more of the details of the lab, okay? For the DC circuits lab. You guys are asking about the questions already for the next lab. We'll do that in the lab. And by the way, on Wednesday, because the exam will go until 11:30, no, the one that's due yesterday, there's no picture that's needed. I'm talking about the new lab. So the lab on Wednesday, the one that normally starts at 11:10, we're going to start at 11:30, okay? Because that's when the exam ends. All right, but just as a reminder, you got to get started early in the labs. And if there's trouble, then we can talk about it. If you do it...
Lumper fee, sorry, for delivery.
I'm sorry? Oh, okay. You got to get started early in the labs, because if you don't, especially on this one where you're going to do a lot of air analysis, you're going to be in trouble. You won't be able to finish it if you do it the same night it's due. It's impossible. If you get 2 weeks, then use the 2 weeks to do the lab. And it's harder because you guys are doing the labs on your own, so you got to get started early. Okay, so enough of that. I want to talk about, so today what I want to do is, I want to finish the example on capacitors and then talk about magnetism. Once I get into my discussion on magnetism, my lecture is going to be pretty descriptive. Meaning I'm really going to focus on describing magnetic fields and some of their properties, and then talk about the behavior of charged particles in a magnetic field. So I will start in Unit 3 today. Okay, there's nothing on magnetism on exam 2, okay? So my objective is to finish capacitor example, basically RC circuit example. Okay? And then we'll start talking about magnetism, introduction to magnetism. Okay, so for the exam, by the way, for the exam to, Wednesday, make sure you understand the process for solving problems. Don't memorize problems. Understand the process for solving the problems and understand the concepts behind the problems. Okay? Don't just try to memorize solutions or different types of problems. Okay, so I have this circuit. And let me blow it up for a second there so you can see it better. This is the circuit, and I want to look at the circuit at various points in time. I want to look at the steady state case and the case at t equals 0. So let me draw the circuit. We have a 9-volt supply, and we have a switch. I'm going to draw it with the switch closed, okay? I'm going to draw it with the switch closed. A 12 kilo ohm resistor. $15 kilo ohms. And then we have a capacitor, which is 10 microfarads, and then a 3 kilo ohm resistor. First question says, what is the current through each resistor at t equals 0? So the question is, do I have to go through and solve this problem, apply Kirchhoff's laws and solve this problem? And the answer is no. I want to ask myself, how does the capacitor behave at t equals 0? I mean, if I have an RC circuit, I have a capacitor and a resistor. How does the capacitor behave at t equals 0? Remember, the current looks like this. At t equals 0, what can you say about the current in an RC circuit? It's a maximum, right? So then it's as if this behaves like what then? What does this behave like at t equals 0? Yeah, it just behaves like a wire. So basically at t equals 0, I can replace the capacitor with a wire. So then, what does my circuit look like? Well, I have these two in parallel, and then I have this guy. So then let me reduce that circuit. I have these two in parallel. I want to figure out the equivalent resistance. Let me get a common denominator. The common denominator is 15. So these two in parallel give me a 2.5 kilo ohm resistor. So then I have this circuit. So 2.5 plus 12 is 14.5. And I have 9 volts here. So my total current is 9 volts over 14.5 kilo ohms. And if you work it on your calculator, you get that this is 621 microamps. So let me write this down. So what's the voltage across? So this is a good review problem, right? What's the voltage across these resistors? So I times R. Okay, so I times R. So if you want to find the voltage across, then you take 621 times 2.5. And you get 1.55 volts here. And 7.45 volts here. I'll write it up here. Since these two, this 2.5 kilo ohm resistor replaces these two, they're both going to have 1.55 volts across them. So then the next question is, what's the current through those resistors? Well, I take 1.55 divided by 3. This comes out to be 517 microamps. And this comes out to be 104 microamps. This plus this has to equal to the total current, which was this guy. Are we okay with that? So now t is greater than 0. What is q as a function of time? Well, first of all, q of what? Let me redraw my circuit. What if I want to find q as a function of time? What do I do? Well, this problem is a little bit harder. This is neither series nor parallel. If I wanted to find q as a function of time, I'm not going to solve this, okay, just because I don't have time. I got to use Kirchhoff's rules, okay? I have to use Kirchhoff's rules. So I have to apply the current rule right away. So I'm going to call this current here I1 plus I2. I'm going to call this I1, and I'm going to call this I2. And so now I'm going to apply the loop rule, and I can apply, I just need two loops because I have two independent currents. So let me choose this loop, and let me sum the voltage drops. I'm going to have a voltage gain of 9 volts. Then a voltage drop of 12 kilo ohms times I1 plus I2 minus 15 kilo ohms times I1. That whole thing is equal to 0. So I'm summing the voltage drops this way. I'm going to do the same thing for this loop. So what do I get for the second loop? Well, let me start here and go this way. Voltage drop, voltage gain if I go this way. Okay, so this is going to be Q. I'm going to call this Q2 because the current through this branch is I2. So I'm going to call this Q2 just for fun. Okay, and you'll see why I'm doing that in a second. So that's my two equations. This looks like a mess, but I1 is dq1 over dt, and I2 is dq2 over dt. And I don't want to write this out every single time. Can I just write q1 dot and q2 dot? Is that okay? The mathematicians put a prime here, the physicists put a dot there. That's what Isaac Newton used to put dots over them. Okay. If it was a second derivative, it would have two dots over it. So then I can write the top equation this way. And then the second equation so then what? What do you do with this? Why are these dq dt? Isn't current the time rate of change of charge? Yeah, we're looking at when the capacitor is charging, right? The current is not constant. What do I do now? Why did we ignore the resistor? Which resistor did we ignore? I see a question that says, why did we ignore the resistor? And why is the voltage drop negative? Drop means right? Delta V is negative, right? A drop means delta V is negative. We're going from higher to lower. That's what literally what drop means. It means that the change in potential is negative. I'm not sure I don't understand the question regarding ignoring the resistor. I'm not sure which resistor I'm ignoring. Can I add the two equations? Yeah, if I can add the two equations and get rid of... Actually, I probably don't want to do that. Because this is going to be a minus 27 minus 12 Q2 dot. So I'm not sure how you're going to cancel it. Okay, hold on a second, because there's all kind of questions coming up. Okay, never mind. Okay, that's good. So let me rewrite it. And like I said, I want to solve this problem, this part. What I would do is eliminate this one. Okay, I would try to eliminate Q1 dot. I would multiply, okay, the easiest thing to do is to multiply the top one by 15 and the bottom equation by 27 and add. Assuming I didn't make any algebra error. Then I would have a Q2 dot. So then if I did that, then I have an equation with a Q2 dot and a Q2. So let's say I did that, then what? I eliminated these guys and I have this and this left, then what? Anybody? Yeah, I would just solve for Q2 and that's it. And then take a derivative to get currents. So what I would end up getting, if I eliminate these two, I'm going to get basically a simple differential equation like the equation I had for the RC circuit. And then you integrate and you get your Q2. Okay, and I'm not going to carry this through here, but you will later on the semester when we do inductors, you will have a homework problem where you actually have to do this. You all have the math skills to be able to do it already. Okay, you've learned all the techniques to be able to solve this already. Okay. But yeah, there will be a homework problem where you have to apply this technique. Okay, and if you want, I can give you the solution. You can practice. I'm not going to ask a question like this on the exam, but just for fun. Because this takes a while to do on the exam. But I went through and solved this. Yeah, let me find my solution. For some reason, I only wrote down Q. Oh. So that's Q1, that's Q2. Okay? So if you want to play around with it, if you have time while you can play around with it. Yeah, you won't see a problem like this on the test. That would take too long. If this was a junior level class, or maybe if this was DE, you might see systems, right? In DE, I think you do these kind of problems, right? You do have the skill to be able to do them, but I'm not going to ask a question like this just because it takes a while to solve it, at least for me. Okay. All right. So I just wanted to illustrate this to you. So it takes a little bit of work to solve this problem. Okay, but and you will encounter problems like this at some point. So the next question is, find the steady state current in each resistor. What does that mean, find the steady state current? So well, we need to understand that. What does steady state current mean? So question, what do you have to study for the exam? Everything from chapters 26 through 28. Okay. Yeah, a long time after the circuit's closed, t equals infinity. And this guy behaves like what? When we reach steady state. It acts like an open circuit, not a wire, but an open circuit. So it behaves like this. Wow, that's easy circuit to analyze, isn't it? So then I is going to be 9 volts over 27 kilo ohms. Did you see the equation for Q1 had a 333 in it? I hope I copied the equation right. Hold on a second. Yeah, let me rewrite Q1 again because I made a mistake. This is Q1. That wasn't Q1 that I wrote, that it was the current. So that's what Q1 was. And so when you took the derivative of this respective time, you get the current. And then when you put in t equals infinity, then this term survives. So that was the Q1. That what I wrote before was I1, not Q1. Okay? All right. So let me erase this. So the current at t equals infinity is that. That's the steady state current. What's the charge in the capacitor? If I put the capacitor here, let me put the capacitor back in. And let me erase all this stuff because we're not steady state. At steady state, what's the charge in the capacitor? Well, the voltage across the capacitor is going to be this here, is going to be the same as the voltage across here because there ain't going to be any voltage drop here. Okay, this is going to be at a voltage, this will be at a ground. So will this point. This point will be at the same potential as this guy because there's no current going through here. So what's the current going to be? I'm sorry, what's the voltage going to be on this guy? 15 times 333. That's going to give you 5 volts. $15 kiloohms times 333 microamps gives you 5 volts. So there's going to be 5 volts across this guy, and there'll be 5 volts across this guy, 0 volts across that guy, because the capacitor is fully charged. So for part D, it's going to be 5 volts times 10 microfarads, 50 microcoulombs. Now I open a switch. What happens when I open a switch after the capacitor is fully charged? Remember the demo I did with the light bulb and the 1 farad resistor, 1 farad capacitor? The capacitor discharged through the light bulb. And so yeah, it will discharge, this capacitor will discharge through the resistor. Your total resistance is 18 kiloohms. And your RC time constant is going to be 18 kiloohms times 10 microfarads, which is 0.18 seconds. So what's the current going to be? Well, for a discharging capacitor, I'm going to ignore the minus sign. This is going to be 5 volts over 18,000. Times e to the minus t over 0.18 seconds. And if you do the math, 5 over 18,000, and I think I have it written down here somewhere. It's 0.278. I'm sorry, 278 microamps. So at t equals 0, this is the current. When you open that switch, this will be the current in here, 278 microamps, and then it decays exponentially. When is Q equals to Q max over 5? Well, for the discharging capacitor, that's the equation. If I go Q over Q max, I want this to be 1/5. To solve this, I take the log of both sides. And so I get t equals 0.18 seconds natural log of 5, which comes out to about 0.29 seconds. Are you okay with that? That's a good question. Where did the negative go? Notice that I have natural log of 1/5 here and natural log of 5 here. Isn't it true that isn't this true? Okay. This problem has everything in the unit, to me. Everything we've covered in the unit is essentially in this problem. We've done series, parallel, Kirchhoff's laws, RC circuits. Everything that's in this unit is in this problem. Okay? Well, I said part B won't be in the exam. I mean, anything but part B can be in the exam, right? Any of them but part B can't be in the exam. Some version of it or the concepts that are related to this problem can be in the exam. You have a homework problem. The last homework, I think it was the last homework problem, is similar to this. Yes, regarding number 14 on the homework. Same process. It's not a problem from the book. It's a problem I made up. Same process. How many times did I use this equation in this problem, really? Except for part B. How many times did I use this equation? I only use it here. That's it, right? Except for part B, I only used the capacitor charging or discharging equation here. Because the rest of the problem, I was looking at the extreme cases. So just remember that you don't always have to use these equations. Because a lot of times physicists will look at the extreme case of t equals 0 and t equals infinity. And students get hung up on the equations and they think they have to use the equations all the time. You don't have to. What happens is students memorize things instead of trying to apply the physics. What is the RC part of problem solving? Isn't this it? This one, right? When we did the discharging capacitor, that was part E. I'm not sure I understand that question. I'm sorry. If you look at part E, that was really an RC circuit problem where I actually had to use the equation. I'm sorry, not part E, part F. Or actually, I should say E and F, sorry. E and F, I used an RC circuit equation. This is for a capacitor that's charging or discharging. This is for a capacitor that's discharging. Okay, so remember, you got to go over your equations. Really, those are the two main equations. Okay, so this is for a charging capacitor. That's for a discharging capacitor. And these are in your notes, so you want to go over your notes. And then this comes from those, so if you could take a derivative of either one of these respective time, you will get this expression. Except for maybe a minus sign for the case where you're discharging. Is that okay? And if you don't know where this comes from, then you have to go watch the lecture from last Wednesday. Because I derived it. Okay. So all these equations I derived last Wednesday. And they're in your book too, so you can look at the book too, okay? I mean, you don't have to watch the videos from last Wednesday, but you can always look at the book. Okay. And the lab associated with this that will actually come later on this semester because you need to learn how to use the oscilloscope first. So we will have something called the oscilloscope quiz, which I'm going to have to actually, I'm going off tangent here, but this is the oscilloscope which came with your kit, and I have to go through and describe to you how to use this, which is tough on camera. Okay, and then you do a lab where we show me that you know how to use it, and then we can use it in the circuit. So the RC circuit lab will come later on this semester. Any other questions? On this problem, because I like this problem just because of how much information is in it. Like I said, part B, it would take too long. Sometimes I would, as a homework assignment, I would add that, but I didn't do it this semester. But you will have a problem like this in chapter 32. You'll be solving a circuit where you're going to have to use this technique, where you have two equations, two unknowns. You have to solve them, and then you have to do the integration. And you see a lot of that in Math 33. In Math 33, you see more complicated ones. Okay, so really that's it for Unit 2. Okay, I wanted to do this example just because it kind of summarizes everything. And what I want to do now is start a new unit. Which is on magnetism. To me, probably maybe the most interesting part of the course because of the number of applications of these ideas. So my lecture now is going to be more, at least for a little while, be a little bit more descriptive. Whoops. Hold on a second. Anyway, so my lecture now will be a little bit more descriptive, at least for the time being. And my mouse is not working, sorry. Okay. So, Unit 3, again, is 3 chapters, 29, 30, and 31. And we're going to focus really on magnetic fields and their behaviors. And we're going to end up getting 2 more of Maxwell's equations in this unit. And I'm going to introduce the first one right away. Okay. So today I want to talk about the properties of the magnetic field. And if I get to it, I'll talk about charged particles in the magnetic field. So the first chapter is, to me, fairly straightforward. And then the second chapter might be the hardest of the 3 chapters because that's the chapter where we actually calculate magnetic fields, just like you calculate electric fields. But this should be a little bit more straightforward to you because 1, you've already covered how to solve these kind of integral problems, and 2, the number of problems we can do is more limited. We're actually very limited as to the kind of problems you can do in this unit. Okay, so there's a lot of videos that I'm going to show you in this particular chapter. I'm going to play them. You'll be able to see them on Zoom, but I'm also filming with my camera, and I can't really, because my film is being put on YouTube, I can't put those videos because they're proprietary. So I'm going to have to actually stop one camera or pause one camera while I play these videos. Okay? So there's a lot of applications of magnetism. Well, the links to the videos I can't give them because they came from the publisher. Okay, so technically I'm not supposed to be able to give them. However, if you watch the Zoom video, it'll be there. Okay, because the Zoom video is not public. It's just for you guys. So some applications are motors, loudspeakers, dusting for fingerprints, MRI. Also, really the real name is nuclear magnetic resonance. People don't like the term nuclear, so that's why they changed the name. The compass, magnetic tape, which is not really used much anymore. The mass spectrometer, which if you had OChem, you probably learned a little bit about it. And the cyclotron. So let me show you these videos don't play within my PowerPoint because I'm using too many resources. So I'm going to run them individually. Uh-oh. Okay. I think I closed too many things. Hold on a second. So I want to show you some videos about the properties of magnetic fields. So I got to pause my video here. And let me continue with my presentation here. So here's a picture. Here's a picture showing kind of what the videos were illustrating. I have a bar magnet. It's a permanent magnet. And the green circle with the little arrow in the middle is supposed to be my version of a compass. And you can see that the arrowhead inside the green circle is the compass pointing north. And you can see that the north pole of the compass is always wants to point towards the south pole of the magnet. And so we say that the field lines go from the north pole to the south pole of a magnet. And they all form circles.
Professor, we're not able to see anything. I think we're stuck on a screen that isn't yours.
Oh, okay, 1 second.
Unless your camera isn't on.
That's possible. Hold on a second. That better? Okay, sorry about that. Thank you. There's too many things I'm changing at once. I apologize. So in that figure, we have a magnet, a permanent magnet and a compass. And like I said before, the green circle is the compass, and then the yellow arrow is the compass needle. And you can see that the compass needle always wants to point to the south pole of that pink magnet. And that illustrates the magnetic field lines. They form circles. Magnetic field lines, I shouldn't say circles, they form loops. They curl. Okay, that's a good term to use, is that they curl. Whereas the electric field lines, they diverge. Here's an example of magnetic field lines due to a loop of wire. And so this brings up the question, what produces magnetic fields? Well, it's moving charges. Moving charges produce magnetic fields. So currents produce a magnetic field. If you run a current in a wire and you put a compass over it, you'll see the compass change direction. Okay. And if we were in class, I would demonstrate that to you. If we were on ground, but I can't do that in this scenario. I apologize for that. So based on our knowledge of field lines, where's the field the strongest? Inside the loop, right? The field is the strongest where the field lines are most dense, which is inside the loop. And they're not really circular, are they, the field lines, except for the ones that are closest to the loop itself. They're not perfectly symmetric. And we're going to learn how to calculate the magnetic field due to that loop of wire later on. So the direction of the field at any point is tangent to these field lines. Here are the field lines due to two closely spaced magnets. If you get right in the middle, you'll see that the fields are fairly uniform. So you can't create a uniform magnetic field. The Earth is a magnet. So this is kind of a picture of the Earth as I'm modeling it as a magnet. You should be able to see the north and south pole of a magnet. Notice the orientation of the north and south pole of the Earth's magnetic field. Do you notice that? When the compass points north, so the south magnetic pole is at the geographic north. Actually, that's not 100% accurate. Geographic north and the Earth's south pole don't coincide. So when you use a compass, there's actually an angle between, it's near, it's not at. There's an angle between geographic north and the Earth's magnetic pole. And that angle changes depending on where you are on the Earth. If you are somewhere on the Earth where there's a lot of iron below you, that compass is not going to be very accurate. In fact, there are some locations on the Earth where there's a 90-degree angle between geographic north and the Earth's south magnetic pole. So you have to take into account where you are on the Earth when you're using a compass. So a compass generally points in the north direction, but not exactly. It depends. It just depends where you are on the Earth. It doesn't necessarily have to be near the poles. The poles reverse themselves because, there's theories regarding that. The magnetic field due to the Earth is really due to what's inside the Earth, and that stuff flows. There's evidence that suggests that the Earth's magnetic field is dependent on the Earth's rate of rotation. And it's hypothesized that the Earth's magnetic field is due to convection currents within the Earth. And because of that flow, you can get flipping of the Earth's magnetic field. I don't know of all the details. The large deposit of iron deep within the Earth, they're molten because deep within the Earth is a high temperature. And really only iron near the surface of the Earth really will affect locally the field. Okay. Yeah, we're not 100% sure regarding to the predictability of the Earth, flipping of the Earth's magnetic field. I would ask a geologist; they would know better, because they specialize in this. So if you talk to the geologist, they can give you a better sense of how much we know. I don't want to say we don't know anything, and I don't want to say we know everything. I just want to say we know something, but we don't know enough about the predictability. So a compass can be inaccurate depending on where you are on Earth. Now, you see in that picture, when you hold a compass tangent to the Earth's surface, it only gives you the component of the Earth's magnetic field that's this tangent to the Earth. There's also a component that points downward too. And I'll try on Monday to bring some demos. Some of the things that we can use to measure Earth's magnetic field is that there's something called a dip needle, etc. If you take a magnet and you put it on a universal joint, it'll orient itself in the Earth's magnetic field. And I'll try to bring one. I have to go to campus to get my equipment, and I'll bring it here. And then Monday I can show you some of that stuff. Okay, we can't do it on Wednesday because we have an exam on Wednesday. Okay. Now remember that when we define the electric flux as something that's proportional to the number of field lines penetrating through a surface. And so we can do the same thing for a magnetic field. And when define the magnetic flux, we can calculate the magnetic flux through an open surface, or we can calculate the magnetic flux through a closed surface. And this one has a unit for it. It's called a Weber. The unit for magnetic flux is a Weber. It's a Tesla per meter squared. And Tesla, and we'll find out, I'm a little bit ahead of the game here, but the Tesla is the unit for the magnetic field. I'll say a little bit more about this, probably not today, but probably on Monday. So if you actually integrate the magnetic field over a closed surface, you have to get zero. If you integrate the magnetic field over an open surface, that thing is a very important quantity, the magnetic field over an open surface. And we'll see its significance in chapter 31. Because it's related to induced voltages. If you have a time-varying magnetic field, the induced voltage is going to be dependent on the integral of the magnetic field over an open surface. Anyway, let's say some things about electric and magnetic field lines. Electric field lines begin and end on charges. Electric field lines can extend to infinity for a single charge. The electric flux through a closed surface is proportional to charge. But for magnetic field lines, they form closed loops. They don't diverge. Magnetic field lines don't diverge. The number of field lines entering a closed surface is equal to those that leave the closed surface. The magnetic flux through a closed surface is always zero. It means magnetic charges don't exist. And so we can say that the integral of b dot den dA is equal to 0. This is one of Maxwell's equations. Gauss's law is another one, so we've already learned a couple of Maxwell's equations already. We will see a couple more. So just to get an idea again how we use flux, I want to do this example. And says that he can produce a magnetic field given by that expression in a vacuum that points everywhere in the x direction, and it increases with x. And we want to use Gauss's law to determine whether or not this statement is true. I will say this, that when you learn Calc 3, no, it's not possible, so we want to show that it's not possible. When you learn Calc 3, there's a very easy way to show this. And I might mention it. Okay, so let me draw the box.
Professor, your screen's frozen on the previous example still.
Okay, so it's frozen.
Yeah, so as the RC circuit example.
Okay, I used to erase the board too. Okay, so it's frozen. Yeah, hold on a second. Darn, okay, I'm gonna have to stop my videotaping and start it again. I have to join two videos together.